So in this installment, we are going to look at work-related graphs. And so our first graph is going to be a force applied and distance graph. So let's do an Oiz-Zerga analysis. The origin, we will set it equal to 0. The y-axis is force applied. The x-axis is the distance. And the intercepts will be dependent upon what we're going to graph. And what we can read is force and distance. The slope is delta F over delta D, which has units of newtons per meter. That's not any quantity that we recognize right off the bat, but newtons per meter is the units of that. And then the area is force times distance, which is newton meters, and that is the work. So what we can see is the area of a force distance graph gives us the work. So let us imagine the last scenario. So the dad and the wagon. Well, what we knew was there was a constant force of 43.3 newtons being applied like so. And so what we saw is as dad applied greater, as he dragged it further and further and further, he did more work. And we can see the area is increasing. If he doubled the distance, he doubled the work that he did. And so that one's pretty simple. It's algebraic for us. And notice in this case that the force is constant. Now we could have a case where the force increases uniformly. And that curve would look like this. It increases uniformly. So force and distance. And so we could read force and distance. The slope is still newtons per meter, and the area is still the work. But now it's no longer constant. So we're now taking the area of a triangle. So the work is the area of a triangle, which is 1/2 base times height. And 1/2, so we've got the base, which is D, times 1/2 the height, D times 1/2 the height, which is F. And that F in this case is the instantaneous F, whatever it is, or the F max. And so if we drew an average F over 2 height, like so, and we colored in that area, well, we of course see that the area here in blue would transpose up to here and be equal. And so what we're doing by finding the area of the triangle is just averaging out that force. And so that's what happens when the force increases at a uniform rate. Well, what happens when the force changes at a non-uniform rate? We have our force and we have our distance, and that might be something that looks like this. And of course, what we're still looking for if we want the work done is we want the area. And as we've seen many, many times before, if we know the function, if we know f of x, we can use calculus to find the area. So we could find the integral of fx dx, or we could use Riemann sums to break out and come up with little rectangles whose areas we can determine individually and then sum. And so these are the work-related graphs, and the most important thing here, of course, is that the area of a force distance graph gives us the work done on the object. In our next installment, 4.0, we are going to be introduced to the concept of power, which is the rate of change